In this podcast, we want to look at ionization energy, we want to define it, and look at the periodic table trends. Now we will begin with the definition of ionization energy. It's the energy that's required to remove the first electron from 1 mole of gaseous atoms to produce a mole of gaseous cations. Of course, it doesn't have to be the valence electron, it can be the electron that is most loosely held by the atom. Now this can be symbolically demonstrated by using M to represent the gaseous atoms. It then will lose its electrons to form the cations, the M+. Now, as with any measurement in chemistry, there would be units attached. The units for ionization energy is measured in kilojoules per mole. That's the amount of energy required to strip away those mole of electrons from a mole of gaseous atoms. It can vary from as low as 381 kilojoules per mole up to a very large value of 2300 kilojoules per mole. Now this is a good time to ask what we think is the element that has the highest first ionization energy. Now if we view this graph, it clearly demonstrates that the first ionization energy displays a periodicity, meaning there's a pattern in the periodic table. Now if you focus on the green columns, they would represent the noble gases, and they stand out as being the ones with the highest ionization energies. Now there also is a visible trend as you are moving along a period from left to right before you hit the noble gases, that there is an upward trend, and it generally increases until you get to noble gas, and then it goes right back to a lower ionization energy at the beginning of the period where we find the alkali metals. And again it leads upwards again until you hit a noble gas and returns right back down to a lower level. You will notice, however, that the noble gases do decrease as you go down the periods. So just to summarize, we see that the noble gases have the highest ionization energies. They form the peaks in the graph, whereas the alkali metals, they form the troughs in the graphs with the lowest ionization energy. Now, we must be able to explain what creates this trend, this upward trend in ionization energy as you move from left to right in the periodic table. It obviously has a lot to do with the atomic structure and how difficult it is to remove an electron for some atoms, where for others it's quite easy to remove their electron. And so this attraction between the electron and the nucleus is what we're going to look at. Now, one of the most key factors that will influence whether we can remove an electron easily from an atom is the attraction it has with the nucleus. We know that the nucleus is where we find the protons, and the more protons you have in that nucleus, the higher the positive charge. So of course, we expect a stronger attraction between the electrons and that positive nucleus. Now another major factor that will influence ionization energy is the distance the electron is found from the nucleus. It has been demonstrated that this attraction falls off rapidly with distance. It has a significant impact in the amount of attraction there is for the nucleus. So the further we go away from the nucleus, the attraction is really lost in holding that electron close. Now this is a good time to introduce a concept called the atomic radius, which clearly demonstrates the various sizes of each of the atoms. As we move from the metals, which are on the left, towards the nonmetals on the right, we can see that the atomic radii are decreasing. That would account for the number of protons. As you move from left to right, it does increase, drawing the electrons closer to the nucleus. Also, we can see that the volume increases as you go downwards, and that would be because you gain extra shells with every period. Now, following from that concept, because there are extra shells, the third major factor is the number of electrons that are in your way and shielding you from the attraction that exists within the nucleus. A larger atom, for example, would have perhaps 2 or 3 shells of inner electrons shielding you or screening the attraction that positive nucleus might have on your outer electrons. Now the last factor that will determine your ionization energy is whether you are an electron that is solely found on its own in your own orbital, or if you are spinning in an orbital with another electron and you're found as a pair. Now typically if you're paired with another electron in the same orbital, you will repel each other, and it's perhaps easier to remove that electron than it is to remove an electron that is found spinning by itself in its own orbital. Now this is a good time to introduce the concept of subshells. You perhaps were told that electrons orbit 2 in the first shell, 8 in the second shell, and 18 in the third shell. Now in reality, there are not just 3 shells. Those 3 shells actually consist of subshells. So the electrons are actually not found on a single shell. They are found spread out amongst those subshells. So if we compare this chart showing some of the atoms and where they find their electrons, we can see that they all have 2 electrons in the first shell, which we call the 1s shell. We then find lithium has its 3rd electron all by itself in the 2s shell. Now in this second shell, which is actually spread amongst the 2s and the 2p, where we find those 8 electrons, we can see that some of the electrons are spinning together in pairs and some are found singly on their own. Now if we just compare helium atom with a lithium atom, we see that helium has the 2 electrons spinning together in a pair in the 1s orbital. Now lithium, on the other hand, has 3 electrons. 2 of them are also spinning in the 1s orbital, or the first shell. However, it's got its 3rd electron on the outer shell by itself in the 2s orbital. This is where the electron will be easily removed from lithium. So in their case, we would see that lithium would have the lowest ionization energy, where its electron can be easily removed when compared to hydrogen. Now when comparing periods, we see that the second period, shown in red, has a higher ionization energy when compared to the 3rd period, shown in green. Now, as mentioned before, what would account for the second period to have a higher ionization energy, as you go from left to right, is perhaps because it has less shells, therefore less shielding, and so the electrons are more attracted to that inner positive nucleus. The 3rd period, having more shells, would be easier at removing the outer electrons, as there is more shielding cutting down that attraction to the nucleus. Now why do they increase as you go left to right? Again, that has to do with the fact that you are gaining more protons in the nucleus, making it more positively charged. Now referring back to the bar graph, we notice that there is a general increase in ionization energies as you go from left to right, but there are some anomalies where we find that it actually went lower in one instance. For example, beryllium in group 2 has a lower ionization energy than boron next to it in group 3. Now that's because boron actually has its 3 electrons that are found in its second shell spread amongst 2 subshells, and so that 3rd electron is slightly further out in its own orbital in the 2ps orbital. And because it's further out slightly, it is easier to remove from the atom. Now, one major trend that was already demonstrated before is that as you move down a group in the periodic table, the ionization energy decreases rapidly. It's largely due to the fact that you now have an extra shell of electrons shielding your attraction to the positive nucleus. And in this case, it would be easy to remove an electron from cesium atom compared to the lithium atom. Now, for the transition metals, we don't really look at any huge trends happening here, and that is solely due to the fact that we are removing an electron from the same 4s orbital, so there's very little difference. The main difference, if you can see there is a slight increase as you go from left to right, is the fact that you do have more protons creating a positive charge. Now you're probably wondering whether it's possible to even remove a 2nd or a 3rd or a 4th electron from an atom. Now we would call this the 2nd or 3rd or 4th ionization energy, and it would be shown using, again, a symbol such as M+, being the cation, becoming a more positive cation, M+2. So now that we've looked at first ionization energy for atoms, how would that compare if we looked at second ionization energies? We'll start by looking at aluminum as an example. We see that the first ionization energy for aluminum to remove its first electron is quite low at 577 kilojoules per mole. As we go further down at removing more electrons, the amount of energy required is extremely large and almost impossible to do when you get to the fourth ionization energy. Aluminum is not going to give away 4 electrons. The number is far too big. What would account for this large ionization energy as you try to strip away more electrons? Well, clearly it has to do with the fact that you are trying to take an electron away from a cation. A cation is already positively charged, and it is not going to let go of its additional electrons easily. And so with this, it becomes progressively more difficult to remove additional electrons from a positive cation. So to summarize what we have looked at with ionization energy, in terms of the periodic table trends, we see that the ionization energy increases as you go from metals to nonmetals. Metals would easily give up their electrons. As you move towards nonmetals, we know that they're looking for electrons and are not going to give them up with any ease. We know that ionization energy is also going to increase as you go up the table, as the atom is much smaller and are holding their electrons tighter. Now, how does ionization energy relate with our topic of metal reactivity? We've already compared in past examples and activities demonstrating that some metals are more reactive than others. Is there a relationship between this ionization energy and metal reactivity? The answer is yes. As we saw with group 1 metals, as you go downwards, they're easily going to react because they have a very low ionization energy. It is easy to remove their electrons, and so therefore they're very reactive compared to metals further along on the right on the table. They have higher ionization energies and therefore are less reactive.